consider us? Alright, on the program, it goes back to its home.
Yeah, so let's just remove to that part.
Oh my gosh, that would be so much.
Waited.
Y'all staying in that
Right.
one.
So it's gonna be first. It's gonna go back to where it's supposed to be. That's it. Go out into, go down, extend, go back to the second. So that's really know what's up.
They don't even do that.
I don't even know.
You don't know it?
What?
You know what?
Now, hold on a minute.
We used to have to do that every single morning.
I don't know that. Knowing the national anthem.
I mean, if I
Say, can you see?
I mean, I'd have to, it's easier when there's other people. So try to find it. Let's see. They're coming.
Hey, how's it going? Good to see you. Good to see you.
Hello. Good to see you.
Look back.
Sitting over here.
Anywhere. Whatever seat's open, I'll sit at.
Everybody situated?
We are.
Let's do this. Good afternoon. Welcome back. We are AGVX, Automated Exploration, and we are presenting the critical design review for our AGV design to you. Mix it up. I'm Luke Clark, the team lead for this section,
And I'm Savannah Tabor, the systems engineer.
and then the rest of our team is to your side, and they'll introduce themselves as they come up. In front of you in your packet, we've got the documentation that we sent out earlier this week, the requirements, ICD, verification tests, all of those include system and subsystem level. We have the project outline document and then an agenda as well, which Savannah's going to go over now.
Yeah, so all of those were emailed as an attachment at the beginning of the week, so don't feel any pressure to do that.
Were there changes?
Sorry.
Were there changes made since you sent something out to what?
No.
Or to the brief itself.
To the brief, slight, cosmetic.
Okay.
So today we just want to go over a project recap from our previous concept review. And then as a company, we want to get across our project goals. And all of our subsystem teams will come up and explain their designs and any improvements. And then we will cover interfaces and allegations between the subsystems, which are mostly defined through the ICD, which you've reviewed. And then we will highlight the project deliverables.
So I took a look at the brief before. If nobody has any concerns with it, I'd like to maybe just skip the slide. This stuff, we went through in technology last time. I don't need to see it
again. So last time, I do want to just point out that last time during concept review, we did have references towards the requirement numbers. We left that out this time since pretty much we come through last time each requirement. Didn't feel like it was necessary again. In the requirements documents though, we have put in our subsystem requirement levels underneath the system levels. And if you reviewed it and everything and you have certain questions relating to specific ones, just let us know. So now I'll just pass it off to Luke.
I didn't mean to steal your thunder.
Yeah, good job rolling with it.
I've been in your spot many times, had to do that.
It's always good to have it in case there's new people or whatever, and then be quick to jump. The seniors are talking about that right now because they've got some new people at their design next week.
Very good. So what we'll show you first then is a comparison of the design we presented at concept on the left, and then the design that we have now with our modifications and updates. The width is the same, the length is the same. We had a slight height increase, but the layout is all the same between the two. I think one major change that you can see was just orienting some of the stuff on top a little bit differently. It helped with some weight distribution and cable management.
Still within the overall height requirement.
Yes, sir. And we'll cover all the changes that we made in detail as we go through the presentation. These are the action items that we took from your concerns from concept. We allocated those to our subsystems, and as we go through our subsystem designs, we'll address how we implemented changes to address these concerns. Did we miss any action items that you can think of? Very good. So I'm going to hand it over to the drive subsystem, and they will explain their design.
Thank you, Luke. Good afternoon. Thank you for coming out again for our presentation. My name is Nicholas Connor. With me, I have Gavin Earhart and Anthony Lear. We are the drive subsystem. And for drives, our need statement was that we should provide a method of safely maneuvering the AGV around the plant, which would allow for the other subsystems to perform their required tasks. For the drive subsystem, this is an overview of our subsystem and the components that we used with that. On the front here, there are two LEGO touch sensors. This is part of our secondary object detection with the bumper. We also have another touch sensor, which is located right here. That is our emergency stop button. And as y'all requested last time, we have added a button onto the end of that so that we don't have a rod that might injure any users. For part of our primary object detection, we have the Sumo eyes located right here, the red object. Combined with that, we have the LEGO ultrasonic sensor on top. And Gavin will cover why we have two of those, but those are primary object detection. On the back left side, this component right here, that is our high-technic color sensor. This is used in identifying all the different cells around the plant. And we also use it in the mixing cell to notify the code when we need to stop for the positioning. On the back, we have two motors. Those motors are connected to our drive wheels, which are located in the center of the AGV. We have it marked here on the two back ones, but in all four corners of the AGV, we have the omnidirectional wheels, which we had in our concept review as well. These allow us to have rigidly mounted wheels and still allow for the turning of the AGV.
Is that the wheel right there?
Yes, sir.
This one, if anybody wants to look at it.
So it was-
Yeah.
And then, as I stated, we have our two drive wheels, which are located in the center of the AGV in line with those motors. Recap from our concept review, a couple of things I wanted to make sure that we pointed out. For our main driving feature that we were working with was the layered base design. With that, we wanted to allow for easy interface, physical interface between the different subsystems. We wanted to lower our center of gravity, so get as much of our weight as we could down to the ground. And we also wanted to give as much height as we could into the other subsystems. Going into this, we knew that mixing had a height requirement of 4 inches for loading their packets. So we wanted to compact our subsystem as much as we could to give them as much room as they need. And then again, the central pivot wheels in the center, those are our drive wheels. Having that allows us to rotate the AGV off the center of the entire AGV and allows better access to both the front and the rear of the AGV. From concept review, we had the emergency stop button that you wanted the button on that shaft, which I pointed out. There was also the center of gravity analysis and the object detection codes. We did not have those fully defined, so we had to find those. And Gavin will talk about that here in just a minute. For the center of gravity of the entire AGV, we have the dimensions of where they are located, and that point is in this circle right here. I have a clip that'll play in just a minute that shows a 360-degree view of the AGV and shows where that center of gravity is located. So I'll let that video play now. And you'll notice this circle in the middle is where the center of gravity is located on our AGV, which is roughly in the middle of our entire device. Some of our details that we wanted to point out here. Between our two components, we have the main base, which is the lower portion here, and the vertical components. And then on the top, this up here is going to be our, what we reference to as the top plate. So in between those, we have a height of 1.84 inches, and all of our components, except for the one you see sitting on top, do fit inside of that space.
So how high does that make mixing their platform?
2.6 inches from the ground to the very top bar plate. So they had the rest of that up to 4 inches to work with. Our subsystem, we have estimated the weight to be 1.1 kilograms, and we will cover later in the slides the allocation of the entire weight that was in our requirements, and we are within what we were allocated for that. For our components, we have 3 that were manufactured here, the rest were purchased parts. As I stated, the base and the top plate, those are manufactured. We did 3D print those out of PLA material, and we chose to 3D print them due to the complexity of their features. And then on the front, right here is our bumper, and Gavin will cover that in his portion. And now I'll pass it on to him.
Here we have our base details and their methods of attachment to allow the molding and mixing subsystems to interface with our AGV. Our team designed the top plate right here that will fit and lock on to the legs right here protruding from the bottom base or bottom structure. They will fit into each of these holes with a tight tolerance. Here, like Nick said before, is our omnidirectional wheels at each of the corners. They are attached to the base structure with a shaft and bearings in their supports. This helps because when the shafts do not grind against the wheels, when weight is put on top of the AGV from the mixing or subsystems. In the middle, again, is our drive wheels, which are connected to the motors right here in the middle and the outside structure of our base. Again, you use bearings right there so that the shafts and Lego axials won't run against the wheel when more weight's on top. Our motors and sensors are all attached to the bottom base except for our primary object detection sensors and our ESOP, which I will show in a minute. The dimensions, the bottom of the lower plate to the ground is 0.26 inches. And as you can see over here, from each side of our AGV, the center line is 3.15 inches. Based on the feedback from our last review, you all wanted to see a side view of the cones of detection for our primary object detection sensors. Here on the top, you can see our Lego ultrasonic sensor, and beneath that is sumo eyes, both attached to our top plate right here. The requirements, we're required to detect an object and come to a complete stop without contact within 3 inches. Through testing, we found that if the sensors were only pointing straight ahead, they would not pick up at 3 inches. So we found that we had to adjust their angle. So for the Lego ultrasonic, we had to adjust 30 degrees, and for the sumo eyes, we had to adjust 7.5 degrees down. So
The attachments, are they fixed such that we don't have to worry about
yes, sir.
checking them and adjusting throughout
Yes, sir.
the website?
And as you can see, as part of the requirement too, it detects 3 inches, quarter of an inch from the ground. Next, we have our top view of the cones of detection. Here in red, you can see our sumo eyes, and in white or gray, you can see the ultrasonic. Measuring the cone of detection through testing for the sumo eyes, it can only cover 5.75 inches, whereas the width of our AGV is 6.3. So to cover the additional spacing of our AGV, we use the ultrasonic to cover the last section.
Why not just use another sumo eyes?
Because it's not compatible with the bricks, so we had to use a Smux.
Yes.
Smux.
With all of the sensors that we used, the combination of them, we did not have the amount of sensors that we can plug into the bricks. They'll be controlling everything. We have 4 ports on those, and we have the 2 light sensors front and back. Those have to be plugged directly in to the brick. We also have the sumo eyes, which has to be plugged directly into the brick.
So you
That
can't
leaves
use
us one more
box.
port, and we have the sensor multiplexers, which all of the rest of our components can plug into. Well, like I said, the sumo eyes cannot, so we had to use a different component for that.
So why not just use the 2 different ultrasonic sensors?
The sumo eyes is preferred. And based off of our use in previous AGVs, that's what we found works best.
So I've got substandard coverage over the gray area is what you're telling me?
No, sir.
Did you really look into ultrasonics?
Yes, sir, we did.
Which one's
And
cost more?
what led you away from it? What led you away from 2 ultrasonics?
With the coverage that we were getting from the sumo eyes and how it functions, we liked that aspect of it more than the ultrasonic sensor. So we wanted to use the better of the 2 for at least part of our coverage.
Yeah.
Still can't afford it. It's always your requirement. On the basis. So the other issue, generally when you're designing something like this, your big issues are you meeting the requirement? And then it's cost and reliability, right? So you want to keep costs down, you want to keep reliability up. Generally, that's where you're going to drive to in this kind of conversations, why you're picking what you're picking. Unless there's a specific performance reason why, it's good to have a certain type of sensor. But ultimately, sticking to one type of sensor is generally going to be better.
Right.
From a cost, economy of scale, assuming you're mass producing this kind of thing.
Right.
And from a troubleshooting, maintenance, sustainment perspective. Go back to the previous slide.
So there was no way to put that sumo sensor where you can actually get the thing.
So the other problem I see here is the minimum requirement was 3 inches. Right, so you never want to unnecessarily force yourself into a minimum requirement. If you can cover beyond the 3 inches this way, then you want to do some of that. So because you want to show, right now what you show me, you've got pinpoint risk there, because if anything is off in one direction, you're not going to meet the three requirement, right? And you've got plenty of coverage, I think, based on the requirements. So I would have pulled that back and say, listen, we're covering beyond 3 inch minimum requirement.
Yes, sir.
Think that way, if things move around, we're still covered.
Exactly.
Yeah.
And right here for our secondary object detection sensor, we have our touch bumper sensor, which is pinned to our base structure, and the bumper sensor, which is a bumper plate made out of acrylic, is connected to each of the sensors with Lego axles. So there's a force on it, the AGV stops. And the bottom of the bumper to the ground is 0.18 inches. And next, I'll be passing the code logic off to Beth.
Sorry, one sec. For the code logic, I'm gonna go over a general overview of the whole code altogether. And then I'm going to get a little bit more specific into how the entering and exiting of the cell works with a little bit of a walkthrough. And then we do have the pseudocode in the background slides if we had any specific pseudocode we wanted to look at in particular. So when we set up, or when we turn on the AGB, it'll start by setting up all the sensors and setting our variables to 0. And then we'll message Brick 2 to make sure they're ready to start their day. Then we'll have the prompt for the operator to ask if we're allowed to begin motion. After we get the okay to go ahead and move, we'll exit the cell, and then we'll begin following the line. And then that'll start our follow the line loop at a set motor speed. As we go through the loop, we're going to be checking the sensors in a particular order, and we're going to be running it constantly while we're in motion. So first, we're going to be checking for an object with either primary or secondary object detection. If one of those two are flagged as being, it registers an object, we will stop and we will do whatever is in the function that is called for the checking of the object. For the e-stop is the same thing. We'll be checking that e-stop to see if it's been pressed and do whatever runs in there. For checking for no cell, we will be checking a particular variable to see if we've gone on long enough around the loop that we haven't seen a cell and it was a concern, and then we would go into the function and stop and flag for assistance. Checking for off the line, we'll just be checking the light sensors to see if they've gone off the line a particular amount. That was a concern, and then we would run into the off the line loop or off the line function. And then finally, we'll be checking for cells with the color sensor. And if we see a color, we'll go ahead and go in, do the functions that we need to do, including entering and exiting the cell. At the very end of the data cell operations, we will prompt the operator for 30 seconds to input the end of day. If they don't respond to our prompt in the data cell, then we will continue to go through the follow the loop around the plant and continue normal operations. If they do input that yes, it's the end of the day, we will stop in the data cell and end our day there.
Where's the charging in on it?
It will be at the data cell at the end of the day.
So how did I get to that first state?
They turned on the AGV at the beginning of the day.
So at some point they turned it off, and that's what this is?
Yeah, so turning it off will be when we ask the operator to prompt us, we will stop motion, and then they can do all of their turning off and end of day processes that they might need to do to us.
So there's really a line that goes back.
Yeah, there probably should be a line that goes to end of day.
Are you gonna elaborate on each of these?
I was only gonna elaborate on entering and exiting the cell, but I could elaborate any particular one if you had specific questions about it.
So what happens if I'm at check e-stop?
So at check e-stop, it's going to look at the e-stop button to see if the button has been pressed, because it's going to be running this loop.
So it's been pressed.
Yeah, if it's been pressed, it will stop. It will stop. It will send a page that we need assistance. It will play. No, it will stop. It will, send a page that we need assistance, and then wait until the operator comes back. And once the operator comes back and sets
And
it's
if
right,
the operator doesn't come back and it goes dead, what happens?
it'll just stay stopped until the operator comes to get us. Any other questions about the general ones here?
So basically, the check object, the check e-stop, and the check for offline all assume that there's going to be human intervention, and even if it sits there till it dies, it's going to require forklifting back to the charge station.
Yes, if nobody comes to help it, it will just sit and wait until somebody does, because if an object is in the way and it doesn't get moved, it will just wait. If an e-stop gets moved, it goes into assistance mode and will wait until operator presses something on the AGV brick. No cell also is assistance mode. And if we go off the line a certain distance, that is also assistance mode. We'll wait until they come and get us. And if they never come get us, we don't continue motion.
So the prompt for operator again for the end of day, that happens where?
At the end of when we've reached data cell, and once we get the word from Brick 2 that data cell has been serviced, we offer the prompt for the operator for 30 seconds to stop us.
And Aren't you also checking for your charge status? How do we know that it's time to charge or not charge?
We were operating under the impression it would be charged at the end of the day. One of our requirements is that we're going to be able to be run for 2 shifts. So we're gonna have enough charge to run for 2 shifts, and that at the end of the day, we will need to be charged overnight.
So in theory, I would want some kind of, routine to check for that and capture that, because I don't want the machine going dead in the middle of the plant. It knows it's not gonna be able to make another loop within some level of, tolerance, and it needs to go back to the charge station and charge. That's just a standard.
That makes sense.
Can we take a time out here? Do you all have any comments for him on that?
Yeah, I was just wondering, I thought the 8-hour shift thing, obviously, we're not about to run this thing for 8 hours. I thought that was a bit of a hand waving moment, so that's why I was confused with this. Because we took the charging station completely out of our equation this semester.
We don't have charging as part of our functions anymore.
Got it, okay.
Given to us as a class.
So that's fine. I mean, if for the sake of simplicity of the project, we did that, that's great, but
Realistically, we would want to have that, yes.
Got it. So I was trying to help you guys out, but Andrew threw you under the bus the rest of the way. If he didn't like that, when should he have spoken up?
Concept review.
At requirements, right? The requirement said it, so from your all standpoint, that's a great example of why the requirements are there. It was hand waving that we did it in the requirements, because we all know the Legos can't last 2
I can
shifts.
get you wrapped around your own axle if you want. So what you're telling me is, you provided me the new Elon Musk batteries that never degrade over time, and this thing will never get to the point where the battery cannot make it 8 hours.
The charging station will never fail. Charge it.
So as long as you did that, you met the requirement. Otherwise, I would let you off the hook for not meeting that requirement, as long as you told me you had some way to mitigate the risk of this thing going dead in the middle of the street.
So I'm trying to think, if we really wanted that, would we have had to have made sure we put in a requirement that they had diagnostics on battery health? Is that what we, like as customers, is that what we wanted to make sure we did?
Sure. I mean, if you're assuming lithium ions, then you basically have to have a battery management system. We'll get into technology now, but, I mean, obviously this is simplicity, so we have to operate, but yeah, I mean, so the issue then is when we say we give you these requirements, the other thing that has to be defined is but for how long? So at delivery, is that it? So does that mean that the second time around, if it fails, that's my fault? That would have been on me to get the requirements in there. This thing has to have at least a 4-year life cycle without requiring new batteries or whatever else might be involved in order to meet requirements, right? So that kind of gets into sustainment, reliability requirements that we really didn't get into.
No. I mean, really, if anyone's under the bus, it's me, like plant manager, because I said, the requirement is it has to run 8 shifts, 2 shifts, never even thinking about, well, for how long? A year, 2 years, that whole thing.
And in a real systems engineering environment, you're also bringing in a lot of folks, your logistics folks, so you're designing for reliability and maintainability. So maintainability might be, okay, we're fine with that. We're going to plan on having batteries stocked and we're replacing them on a 2-year basis. And that would be considered in your entire cycle. You were really developing this.
The use plant manager said it has to run 2 shifts, right?
I did. And then we would plug it in after that.
Right, so that tells me, but you just said that this thing ain't gonna run 2 shifts.
No, it eventually will not run 2 shifts because the batteries will degrade over time.
Right, and in Lego world, it definitely won't run 2 shifts.
It'll run 2
Therefore, it has to run 2 shifts, at some point, it's gotta get recharged.
Yes. So what was in their operational scenarios is our operators would plug it in after the 2nd shift.
Correct. Yeah.
And it would charge.
All right. Give Been heard enough time.
No, I'm thinking it's a great point.
No,
So from a customer standpoint, I should have thought of that from like the systems engineer company designing it for me. You all also could have thought about it and say, hey, you know, we need to have some battery health in there. To really meet what they're asking, we need to have this in there.
or we should ask them,
Ask
do
them,
you
that's
want
right.
battery health in there? Because otherwise, you're not gonna know exactly when this thing's gonna not make it around the track anymore. Might be 2 years from now, might be 3 years from now.
Right. Never even thought about that.
But the reality is with lithium ion batteries, you have to have a health monitoring system. Okay. cool.
Yeah, thanks, Russell.
That was fun.
Any other specific questions about the code, in any of the functions?
No, and I think, you mentioned going through the pseudocode. From a critical design perspective, I don't know that that would ever be necessary. Because I don't see anything here where I'm concerned about the ability to do that. So I would imagine if there's anything that's gonna get uncovered, it'll get uncovered during test. And it'll just be some logic changes to the code. And we should be able to get that working without. So at a critical design review, I'm not gonna be too concerned about looking at syntax or even pseudo syntax for logic. Unless you had some artificial intelligence going on in there and it was cutting edge stuff. Then at that point, we'd be like, wait a second, you're relying on AI to do some of this stuff? Then you're gonna have to make me feel comfortable that is gonna work, it's been proven, and it's not gonna be a high risk factor for the success of the program. In this case, we're basically looking at up down, we can do that all day long.
Yeah. Maybe other than this, like me personally, that was my hang up. Do you know how you're gonna get in and out with the technology you have?
Well, it's good here, I could transition into that, little bit of a walkthrough of how, we plan to get in and out of the cells. That's all right. So I have my AGV model. This is a scale model of our AGV. This is gonna be the front half and the back half. Light array 1 is gonna be the one in the front, and light array 2 is gonna be the one in the back. Those are the references that I'll use. So the reason that we really wanted to utilize the pivot wheels when we were turning into the cell, because it would make it really easy to center ourselves if we could pivot easily. So that's why we took a lot of time thinking about how to get in and out of the cell, the enter and exit functions. And we also only wanted to have one function for entering and exiting that changes based on what direction we wanted to go. So as we're coming into the cell, the dimensions, this is the restricted section and the aisle. These are figure 2 in the ICD if you wanted to see what the dimensions actually are. It should be to scale with our AGV box thing that we have. So as we drive in, the color sensor that is approximately here will see this color space, and it should be lined up with this line. Our center wheels should be lined up with that line. And when it determines whatever direction we need to go in based on the color, for example, if we are at the molding or data color, we are going to turn it forwards. So we are going to slowly turn until light array 1 is no longer on the line. Then we are going to go just a little bit further, so it's really not on the line. Then we're going to continue turning in that direction and stop when it sees the top line. Then it will slowly center itself and then pull forward until the bumper hits this cell wall of either the molding or the data. If we're backing in, we'll do the same thing, but with light array 2, turning the other direction. So slowly come around until we're off the line, gonna come back around until we get to this line, then back in until this color sensor at the mixing cell is indicated, and then we should be lined up so anybody could do any servicing that they need to do at their cell.
So how sensitive is your routine to the placement of those colors?
It should, well, I'm not 100% sure. I know when doing testing with the color sensor that it could pick up a very small shape. So we could, as long as we have.
I'm worried about the position. The position of that color. So earlier you said you went over and it detected the color. And when it detected the color, it should be in direct line with the aisle. So that means that the placement of that color square or whatever it's going to be has a specific position it needs to be in.
Yes, so
How specific is it?
I'm not 100% sure.
So that's something that we're gonna need to address, because long after you deliver this and leave, we've got to maintain these things, right? We need to know exactly where they need to be on the floor in order for this thing to work.
Yes, it's gonna be part of our testing to make sure we have the cell locations. Both pieces are in the right spot so that the color sensor will see it every time it goes past.
Yeah, but I need to know that too. I need to have some
Yes.
documentation that tells me from scratch if I painted my floors, which
Yeah.
OSHA makes me do every 3 years. Where do I re-put them? Unless you're trying to be like Lockheed Martin, so that we have to come back to you and get massive contracts in order to be able to paint our floors.
That was not part of our plan.
Okay.
So that was pulling into the south, so now coming back out of the south, depending on which direction we've gone in, you need to go the opposite direction out. So if we backed in, we need to pull out. So when we're pulling out forward, we're gonna go until light array 1 no longer sees the line. Then we're going to turn about 45 degrees in the direction that we need to end up going. And then we'll pull forward until we see this line. And then we will go back to following the line function, which should center us back up according to the code as it's written. If we're back,
What if it doesn't?
I know, I should have said.
Okay.
It will. I caught myself.
It will every time one should have done. So you've got no mitigation for if it doesn't happen.
You mean when it comes out? Not yet.
So it'll just keep driving until
We do
it hits
have
the
that.
wall and knocks the building down.
We do have that in our code. There is part of the function where the light array that is in use does not detect a line for over 2.5 inches. It will stop on its own and
So
request
that
for
routine is
assistance.
built in, overarching routine for all your, for
That's in,
anything.
that's in the
Is it-
follow the line. Anytime we're following the line, which eventually it will start following the line. Anytime it does that, it will follow that. Sorry. So backing out is when we pulled forward, so now we need to back out. So what we're going to do is we're gonna read light array 2 until light array 2 finds a break in the line. Then we're gonna switch to reading light array 1, and we're gonna do the pulling off the line until it no longer sees it, and then pulling around until it sees the bottom line, and then going back to following the line after that.
So when you're pulling in, one of the things you're doing is, when you're coming in, you're trying to capture the line as well.
Yes.
And that's, you basically go into a follow the line routine at that point, but it's really a different routine, I'm assuming. So in that routine, is there a fail safe that says if you don't see the line in so many inches, you're gonna stop it? Shaking your head, I don't.
We have not written the code, but we will have that in there.
Good answer.
Any other questions with entering and exiting the cell?
No, thank you.
Here is a summary of our verification tests. We are gonna test everything from normal operations so that we can test all of our sensors and all of the functions that they're supposed to do, and make sure everything is working in tip-top shape. We did send these out to you. Did anybody have any concerns about our tests that they wanted to discuss here?
So these tests are run before you get to finals?
Yes.
So these are your internal tests, right?
Yes.
D5C,
Yes.
motion pushed off of the line. What
So
exactly is that?
we're gonna be in motion going around in a circle, and we're gonna push it off the line a little bit to test and make sure that it will either come back, or if it's gone too far, it will stop if it misses the line.
You got a flat tire. Well, the union folks got mad that they're losing their guns with this, and they start trying to push it over.
Sure.
Make sure it comes.
So the only thing I want to add to this is, I'd like to see, I'd like some verification that it will stop if it doesn't see the line. So again,
That I believe is covered in 5B, so in our requirements, it is a break of 2 inches, we need to be able to get back on the line and continue motion. If it's any farther than 2.5 inches, it will stop if it no longer sees the line. So the test where it has a line break of 3 inches, it should stop in every time we do that test.
All right, I'd like to see that going into a cell as well.
Yes, sir.
I don't want you running over my cells just because we have 30 floors.
Yes, sir.
Maybe testing your like emergency stop.
Yes, so that we're going to test that during normal operation servicing. We will, every time, we will take one opportunity to press the emergency stop and make sure that it goes back to rights afterwards. And that is, more details are given of the verification test in the requirements documentation at the end. Anything else for verification tests?
Based on your concern about placement, Russell,
Yeah.
we want to test of how far that color sensor
Where these
can
need to
be
be
placed
located?
left or right. Because it's going to eventually try to pick up that other line, correct?
Yes,
So once it turns, so you just need to make sure it, when it turns, it can pick up that line.
yes. So add more self-maneuvering tests.
I guess another thing that I would want before we snap the chalk line on CDR is I want you to tell me the position of that colored block and the tolerance. The tolerance is plus or minus 3 microns. Then this, I'm not going to be able to sustain that. If it's plus or minus a few inches, then I think that's.
So I'll just take a time out here real quick. So Nick, do you have any educated thoughts on how sensitive it will be to that position? That you would want, if you did, now would be the time to discuss it. Because if not, you're not going to pass CDR. Oh, but only if you think you have some educated thoughts that would make
I do have
sense.
some that would help with that.
Okay,
Since we are going to where we're looking for the line, there will be some play in that. I don't know how much extra room we have around it, but there would be some, if we're ahead some or behind some, since we're turning and looking for that line, as long as we're not too far off, up or down. Now, we haven't done any testing, so I don't know what those values are, but I do not think that it would be a very small number, like you're saying in the
I
micro.
don't either. You're really just gonna follow an arc until you get the line, right? So
Yes, sir.
as long as you don't stop too soon,
Right,
stop too soon, you'll never see the line.
right. But then it would go into, like you were saying, you wanted, where it doesn't find the line, it'll stop and request for assistance.
So it should be pretty easy for you to tell us what that is.
Yes, sir.
So it should be some plus or minus off the line, plus or minus off out.
Yes, sir.
thank you.
You're welcome.
If that's all the questions for drives, we're gonna go ahead and pass it off to the mixing subsystem.
Okay, we are the mixing subsystem, already met. And then we have Matt, of course. And Matt is our subsystem team lead. We have defined our need statement that the mixing subsystem will receive, store, and deliver packets in such a manner that the available packets that are being delivered to the zone never run out. And here is a view of our subsystem on the whole aging body. I'm gonna go through a project recap from the concept design review. This should be a familiar image. And here's our components here. From concept review, we took down some action items. You all had a concern about our chute and whether those packets would freely maneuver down the chute without any interference with friction. And also glancing back to our concept design, we had like a funnel here that was really tight spaced, and there was a concern of whether the packets would end up getting jammed through there. Internally, we took action items as well. Number one being to clear up that redesign of the packet chute, and number two, to finish defining our design of how we stabilize our packets that go on top of our conveyor belt design. We also needed to finish defining and designing our base and structure, and also how we were attaching the bricks and hardware on top of our subsystem. So I'll start with a big picture, breakthrough components of our design, and then Luke is going to go over like our design improvements and different accomplishments. In the green, you can see our base and structure is slightly changed from concept review. We are still using the 2 Lego motors, and those will power our 2 conveyor belt systems. We are still using a 3D printed conveyor belt out of a flexible TPU material. We are doing 3D printed conveyor belt tension wheels, and we have our conveyor belt drive wheels, which are hidden in this view behind the conveyor belt. We're also using alignment pins to help us attach our conveyor belt system onto the base. Here's our newly designed chute. Luke's going to go over those changes. And we are also using Lego connector pins to help us assemble onto the platform in which Stripe's discussed to you about. Adding on to that bottom layer, we have our top layer, seen here. And that is because mixing has took over the responsibility of the attachment of the hardware for the AGV, such as the bricks and the smokes that drives are using and a battery pack. With that top level design, we have designed a packet stability here, which is composed of like acrylic doors, a hinge mechanism, and a latch. Luke's going to get into the details of that as well. We are using those same Lego connector pins as we did down here to attach the top level to our bottom level, and of course the hardware on top. And if you look at the yellow placards here, we have also taken the responsibility of the ANSI labeling for the requirements. And now, if you would pull up the CAD model, and I'm going to pass it to Luke.
Just going to give you kind of an overview as he pulls this in, a 360 view of what we've got going in our design. So like we discussed, the bricks are still facing outward for the operator interface. That was one of our requirements.
Okay, hold right, go back, Nick. I want to see, no, like, keep going. I want to see, yeah, how you're holding the bricks in.
Oh, yes, and I've got some more
Gotcha.
pictures that I can show you. About that. So the stuff on the top is fastened in a couple different ways. The bricks have to be easily removable, so we use Lego pins to attach those. The requirement was that the batteries on the NXT need to be changed in under 3 minutes. So we accomplished that by making it easily removable, so you can change those batteries. Thank you, Nicholas. Okay, go back to the presentation now. So the first and major concern that we discussed was the chute, and on the left you see that preliminary design option, which was very narrow coming in and then awkward angles for the bricks. So our redesign of the chute is opened up, and I'll let you all hold that and see it. So we opened up all that space to reduce the walls so the bricks would not get jammed up in the chute portion. One concern that we had as we started to test was that the bricks would just land on the 2-inch square and bounce off. So the plastic sheets that you see taped on the front will prevent the bricks from popping out toward the front or the side. In the actual mixing cell, there is a back wall and a plunger on the left, so that covers the 4 sides of that. So that's how we handle that concern. Another concern was that the wall height was just not quite tall enough on the last shoot. And so we raised that to 1 inch. A brick is 0.65 inches tall. We increased the hole as shown here to accommodate the longest dimension of a brick, which is 1 inch, and the hole clearance is 1.2 inches. So brick can freely pass through in any orientation. The other thing you'll see on the chute is the 2 slots. You can see them well here in the side view. And those just slide into the slots we'll have. This is a prototype. We'll have slots there. And it makes for easy assembly or disassembly. So when you lift it on the fork truck, you can take that chute off the back and decrease the width so you could fit it in a tighter space if need be. And as Savannah addressed, we've got the top plate, which provides packet stability on the top and insides, and then the acrylic door is on the outside. So when the operator needs to refill the packets, they can simply lift up the door, and it's got a clip attachment, which I'll have Nicholas pull up here, and I'll show you a little closer here. So as the door swings up, this handle fits over this attachment here, and it's got the tab, so it'll clip in, and when the operator is done filling, they simply pull the tab back and lower the door. So the top clearance between that ceiling and the brick is 0.1 inches. What I've shown here is if a brick needed to tip over forward, it would have to go through a gap of 0.2 inches. So it covers that. Over backward, I forgot to put the picture in for that, but the distance would be 0.15. So that would also be covered in that clearance thing. So on this prototype we have, you can kind of see the clearance going on between the bricks and that ceiling. So even when you tip it forward and backward, they have nowhere to go. We did not have the doors on this, but there is the inner wall and that top ceiling. So the other thing is this base assembly that we've got. So this holds the 2 conveyor belts. The motors can mount in the middle here. The interesting thing with this is when you need to disassemble, all you need to do is pop the conveyor belt out like this. We've got the angled slot there, so that makes for quick and simple assembly and disassembly. The pillars you see on the corners have holes in both the top and the bottom. So for the bottom, we'll be attaching 2 drives, and for the top, we'll have the plate, as I just took off there. And then the slots, as we discussed already. We went through various iterations of our belt in testing. So we came upon this, which is very close to our final design. And you all held this last time, but we came upon the desired thickness that gave us the performance we needed and our slot width. And we designed that so that the slot width would actually hold the brick. So that helps with the stability as well. It grips it in. And then our wheels, we designed to fit with those as well.
So you increased the thickness, or you did not increase it?
We increased it very slightly from the last design. We actually went slightly skinnier to see, but we realized we didn't need that skinniness anyway. And the thickness provided a little more durability.
So the tight tolerance is in there between the belt guides and the back wall, the top wall, and the acrylic cover. Any concerns about loading the bricks?
We have had no concerns with loading them. With this prototype, we were able to see how easy or difficult it was to put them in, and we didn't find any challenge with the loading that.
So there's no way to get them too far in and jam up against the wall, or
not that we found out.
rip open powder and dump it all inside.
These packets, we found when we were touching them, they're pretty rigid.
Yeah,
I don't know if you could really break that open at all. And I'm notorious for calling them bricks because they're Lego bricks. And every time we practiced, they said, call them packets. They're packets. And I just kept saying bricks. So if I say that, that's why. I just can't get it out of my head. So the other thing that Savannah was talking about was the brick attachment on the top. So this is our top plate. We've got the holes for Lego pins that match the shape of the brick. So this enables us to take them on, put them on very easily. And the ANSI labels, we showed those here. We needed to label the forklift points. We needed to say that we are an automatic vehicle, and we needed to have no writing signs on two opposing sides of the vehicle. So we chose the right and left side for those. Any questions so far? So I'm going to hand it over to Matt. He's going to discuss some of the prototyping we did.
Yep, so once we had our design, we built this prototype you see there out of acrylic. And we did use the 3D printer to do the wheels and the belt. We created just the generic code so that we can just see how it looks when it's dropping bricks and kind of understand if we were going to have any issues from that point. Through that testing, we found that we could successfully drop them in the 2x2 square and that our experimental weight was 1.35 kilograms. This is going to show that test that we did. And also in between each packet being dropped, I'll go over this a little bit later, but there is a 3-second pause. And that's so that the first one can clear out the way.
That was your first test?
Yeah.
Were you scared that that black one was gonna fall when you didn't want it
Yeah,
to?
we did. We have that angle down now. We did an arc length formula, found out exactly with our belt thickness and everything what it needed to be. It's 72 degrees that it needs to turn to drop one. And I think when we tested this, it was at 70. So eventually it would have dropped 2 or missed 1. But yeah. Now I ran the other day 16 on each side back to back, and it lined up perfectly every time.
You guys did testing that showed that you were gonna need this, is this what kept you in the 2x2?
Exactly. Yeah, when we dropped them before without that, they would, some of them would land where they were supposed to, but most of them would bounce and travel a distance of an inch or 2.
That, we can use on there now. Can you show your, go back to your,
I think in this one, we already had that on there.
yeah, you do, but
Yeah.
watch, play again. Don't know how the 18-wheelers drive down the road, but you see how what their little flaps look like?
Yes.
I have to plan for making sure I'm using that.
We considered it a good alternative because we have to back up. We've got this 1.5-inch wall. So we wanted to get the chute as low as possible and yet have that stability. So having this flexible material, it passes freely over there. And yet we can still have that control of where the packets go. So understandably, it will be a maintenance thing over time, but we considered it a good alternative.
So we'll go through some of the design logic, how our system's going to work. So originally, the first brick, brick 1, is going to send out a message that it's made it to the mixing cell. That's going to go over into the molding function. The molding function is the main one on brick 2. Our mixing function is kind of nested inside of that. So once molding receives that message, it's going to call on the mixing function. The mixing is going to request the packet recipe from the mixing computer. It's going to acknowledge that message and wait 5 seconds before sending the packet recipe back. The mixing function will then acknowledge that they received it, and it's going to start to do the process of delivering those packets. So first, it's going to recognize how many packets of each color that it needs for the batch. Then it's going to check for e-stop So it's gonna check for e-stop. If there is the button pressed, then it's gonna wait until the operator resets it. And it is going to check for e-stop in between each individual packet dropping. That way, because there are moving parts, it'll be stopped if there's any issue and not continue going and risk hurting somebody. So the conveyor belt will move like we saw in the video. It'll deliver a packet, wait 3 seconds for it to get cleared out of the way. It's going to repeat that until all the packets are done in that recipe, and then it's going to globally store that so it can be delivered to the data computer layer. After it does each batch, it's going to determine if more packets are needed. If there's less than 2, it's going to page the operator, and it will wait for them to fill it. Once they've filled it, they have to press a button for it to resume. So once they've pressed that button, it then exits out the mixing function back to molding, who then sends a message to the drive's computer letting them know that mixing is done and they can continue operation. And this is our verification test, which like we said before was in this documentation. Basically, we're just going to run through scenarios with normal operations. We're going to simulate getting a message, simulate sending a message, run through different batches of different numbers. We even have one where there's actually 0 for that batch because that is a possible scenario. And we will be pressing the e-stop button in those randomly just to make sure that it will actually stop when it's supposed to. Do we have any additional questions about the verification test at this point? And now we're going to switch over to the molding system.
Good afternoon. Thank you again for being here on a Friday afternoon and Good Friday at that.
Oh, thank you for saying that. I totally missed that this was Easter weekend, or I would have never scheduled the review today. So I apologize to everyone. And thank you for acknowledging that, William.
I'm William. This is Andrew Paget. This is Eric Meredith. And we are the molding subsystem team. So our subsystem will detect, measure temperature, and record the states of any ovens present at the molding cell. Subsequently, it will transfer all data, including the states of the ovens and mixings data, to the main computer at the data cell. Over here on the left, this is where we're at concept. This is our design now, and we're going to get into the details shortly. We did take a couple action items. First one was the precision tolerance for the height of the oven. That was on one of the slides in concept review, and we toleranced it to the 10,000th of an inch. Not realistic. Took a lot of heat for it.
So,
Yeah.
We rectified that with the ICD. Second one was we didn't actually have documentation for permission to use our non-permanent enabling device. That was a handshake with the plant manager. We talked about it, but we never documented it. So that was a problem. So we corrected that in the ICD. Okay, before we get into these details, we'd like to take you over to the table and just do a small demonstration. So what you're going to see here is the last time that our signal light turned around on the ovens. This time we want to show you our arm actually swinging out and inserting the thermometer.
Hey, Russell, can you move left just a little? I think I can actually get your demo on the recording.
I got some really good videos of
All
this.
right.
What's actually going to happen once I run our code, which we'll talk about later, is the arm is going to come to its stationary home position and then simulate. It's going to go to oven 1. Right? It's going to insert the probe. It's only going to pause. This is going to be quick. We're not actually trying to read temperatures right now. It's going to pause for a second, come back out. Before every big movement, you're going to hear an annoying sound saying, hey, get out of the way, something's moving. It's going to do the same thing for oven 2 and oven 3, and then come back to home. Say it again?
Yes.
Yeah.
Okay. Yes, so we are gonna cover that. That's why we need the funnel, just in case it's not in the right spot where we define for them. And the funnel will take it right in. Little,
So what's the diameter of the hole versus outer
It's
diameter?
5,000 to play on both sides.
Both sides.
So yeah, 5,000 all the way
So if it's off, what happens?
around. Eric's gonna get into that in a bit. We have an enabling device that eliminates any inconsistencies, as was discussed earlier in your tolerances within the area in front of itself, with the maneuvering the drive space.
So remind me, this thing is not sensing the location at all, right? It's completely based on everything being in the right position at the right time,
correct. Okay.
which creates a lot of risk that we're mitigating with our funnel.
Correct.
So how much play is in this? Is that designed in? I mean, if you're hitting a funnel, something's gonna have to give, right? Where is that?
So it does give when it's off. Yeah, it hits the funnel, and he'll get into it, but it does slide because of the nice round piece. It slides, and it's being so far out, slides a little bit, comes back, doesn't throw
You
it off.
fixed this hard, right?
Actually, I will get into the sliding grooves, but the temperature sensor is actually not fixed whatsoever. It is dimensionally placed between there to allow for slight axial or movement in any XY direction, only when it's extended though. Because when it's further out, there's less rigidity, given why there's no support here. So it actually allows for a bit of,
You're gonna get into the
yeah, I get into all the
groove
Yeah.
stuff.
literally.
All right.
We just wanted you to see it in motion before I verbally explained it in motion because it's much harder to conceive than just seeing it. We broke it down into 5 main areas of improvement. Here you can see our overall dimensions, the height, width, depth, and our most critical dimension, the height from the drive space to the tip of the temperature sensor, which is why you see it in tolerance. Specifically, this places at the exact height of that hole so that we can interfere with it correctly.
So what'd you say the tolerance of that is?
Of this one here, the tolerance of the hole over there with the
The
temperature.
tolerance of that place.
Your design phone. I'm sorry, I meant to say the specificity of it compared to other dimensions. The reason we have it more accurate, which is actually why in the next slide I'll show why we picked acrylic as our support material because of the preciseness of the laser cut.
What is the tolerance?
Of which dimension?
Yeah, plus or minus.
It would be the same tolerance as our hole, actually expanded much so by our enabling device later on. So realistically, 1/2 inch. So given our funnel. The funnel has an inch diameter. Yeah.
Do you have a 1/2 inch of movement in the actual thermometer itself? Like, can it raise up, if it's a 1/2 inch low, can it raise up a 1/2 inch and still go in?
Oh, I see what you're saying. Does it have that much movement at the tip?
Yeah, does it have that much movement at the tip?
So we haven't gotten enough testing as far as it being inaccurate because we have it accurate at the moment, of course. But Eric's going to get into our funnel design and why it has 2 different slopes. First being shallower and guiding it in
Gotcha. I'm just wondering, you said the tolerance was a 1/2 inch, but do you have a 1/2 inch amount of movement that it would actually give that much to still go in? Or would it bind because you don't have a 1/2 inch? It's mounted rigid enough, you don't have a 1/2 inch of play.
Understand what you're asking. So when we tested with the funnel and it being offset, it did guide it over and enter the hole still. Piece right here.
But your manufacturing tolerance wasn't off by a 1/2 inch.
Right.
Andrew said it could be off by a 1/2.
I was saying, given the funnel factor, yeah.
Right, so that
As far as the actual, yeah, as far as actual tolerance of how far the tip of the sensor can move, we don't know specifically. It's really just,
You're gonna wanna know that all the way through. If you really do have a tolerance of 1/2 inch, I don't know why you're measuring, just that specificity, I don't know.
I thought you were referring to the, as far as what's our tolerance missing the hole. I'm sorry, I didn't know you were referring directly to the.
Well, what you're showing me here is design tolerance or design specificity, right? So you're saying that that thing needs to be 4.66 inches, so which that doesn't make any sense if in fact it can be plus or minus a 1/2 inch.
Yeah, and I realize now you're referring directly to that tolerance of this number. I thought you meant the tolerance at the right.
So- right, so ideally it's made so it's gonna be at the right height, always. But the funnel's there in case drives doesn't quite get us where it needs to be. If something happens to the AGV, it's a little bit off. Right,
So,
but nothing happening, it's gonna be right where it needs to be.
Again, taking a timeout.
Okay,
We all know it can't be right where it needs to be, right?
right.
Because every manufacturing method has plus or minus. I mean, that was his original question. What's the plus or minus on that height? And
We could definitely add it.
right now, your design requirement is based on the assumption that you're gonna work without the funnel. So you're saying you're at 4.66 inches, probably plus or minus, what, 100? Then how does that work?
How big is the hole?
Yeah, well, 5,000, so you get 5,000. What's your? I know what you said.
Yeah, that's how much.
Your radial tolerance. That's plus or minus 0.005.
That would be interference.
Yes, yes, right, is that what you're touching? And then we introduced this,
The hole is plus something minus nothing. The hole can be small.
yeah, you need to know the tolerance of the hole too. Because that hole, it can vary. So if it's, I don't know if y'all measured it, it's probably what, quarter inch plus minus something, right? So you wouldn't get in all that. It's not a design class necessarily, so we don't want to get too carried away with it. One thing that from a design perspective that I would really be looking at, because I know you can get, I don't see a precision here that's so precise that it's unmanufacturable. But what my concern would be is you're banking on the funnel to guide the probe into the hole. But where is that variability designed into the whole system? I don't see any elastomeric mounts. I don't see anything like that. You're just bending the hell out of a probe, is all I'm seeing. So that's, obviously we don't want you to go do all that. It's a little bit crazy, but you should be able to talk to that. Or in a real world scenario, you would show that we have designed the system such that the end of the probe can move in this vicinity, and here's how we're compensating for the lateral forces without creating strain on this component. Otherwise, we're gonna have cracking, we're gonna have pressure, this thing's not gonna last very long. Or the funnel's gonna start cracking. Which it may anyway. So all that would have to be kind of talked to. Because I'll tell you right now that that's the ideal state, which will never be.
Yeah, I apologize for that misunderstanding. As far as the ability of our manufacturing to achieve this for our subsystem, this exact dimension, if I'm not mistaken, I believe the laser cutter is given the radius error of the actual laser beam, pretty sure we're down into the thousands there, so.
But again, you don't really need that kind of precision with the phone. You just gotta demonstrate that you can flex.
Yeah, that's right. My
Flex is the real issue, how much flex is?
Yeah, we can definitely tack that on to our testing because it's something that we assume that's gonna happen. All right, thank you. Moving right into the first part, we're gonna look at the structural design, where the upper level is made up of the pivot arm that you saw do the actual rotating. The lower level here is made up of our support structure that is allowing us to achieve that desired height, as well as the servo motor responsible for turning this pivot arm on the upper level. This lower level down here as well also is interfacing with the drives platform, which we'll show in a little bit more detail later, better view. And as you can see here, this is space that was allocated for the drive subsystem, the inner workings. They needed to put that on the upper platform, so we made sure to design our subsystem in a way that we can work around that space.
So this is all your subsystem here.
Yes.
But the reality is, whatever tolerance you come up with for that height has to translate from the ground up.
Yeah, so they would have to meet their requirements.
It has that tolerance been introduced to your subsystems, your other folks as well.
I mean, they have their own requirements.
You're creating the tolerance restriction right here. So they have to match that with theirs, otherwise you can't come up with yours. So if theirs is 4 inches and 5 inches, yours is 4.66 inches, that ain't gonna work, because they're doing theirs plus or minus, it's sloppy.
I see what you're saying. I was referring to, we were handed a requirement stating that they were gonna put us at 2.6 inches, so we'd have to assume that that's tolerance there.
The biggest thing in mechanical engineering is geotolerances.
Right. I don't think any of us thought that you need to put a tolerance on that 2.6 for them.
But we definitely do understand that.
Oh, yeah, makes,
That
as
makes
soon as Russell
perfect
said it,
sense.
it's
In
like,
the back of my head, I was
yeah,
like, they're
that,
required to do
that is not on anybody's radar.
Which actually takes you right down through the wheels.
Right. Right.
Are they pneumatic?
Wheels, Nicholas.
Are those pneumatic, the wheels you got in the center? In reality?
The drive wheels?
Yeah. Good answer.
All right, is there anything else you want to see on this one? You'll get a bunch of other views here in a second.
Wow, I just want to take the time on this for a second. That's crazy, isn't it? You talk about interactions between subsystems. It's like, you know, what a cool idea, all this, everything, but it's totally dependent upon the tolerance of where they're getting you to make this really tight one.
Yeah, so in some systems, you know, there's certain points where you can't control tolerance anymore. Pneumatic tires, for instance, I mean, just the temperature in the building changes and your height may change, you know, an eighth of an inch. Right? And that's well past your tolerances. So you may be spot ass on, but the whole system's moving up, down eighth of an inch. So on a cold day, we're nailing it, on a hot day, we're missing it by a mile. So that's gotta be kind of considered in any systems design, right? Who's driving the most specificity in the design requirement? And is everybody else trying to march to that? So that's the only. But again, we kind of mitigated that with the fund.
Yeah, which is where we like to take the justification for the final comes. So, all right. Yeah, I wanted to highlight that because it is a driving factor behind a lot of our design features, as you're about to see, as far as space allocation. So moving right in, our support structure is laser cut from acrylic, tolerance reasons, rapid prototyping reasons. This intermediate platform you see here has been lowered by 1.5 inches in order to not only achieve that height, but given this upper level dimension here, we still needed this servo to be able to rotate over top of that platform without interference, obviously, in order to create this balanced beam that is allowing us to do this extension. This layered design here is allowing us to basically sandwich the temperature sensor as well as the compound rack and gear system between these two layers of acrylic, and then seating bearings in each layer in order to create these frictionless axis of rotation. Here on the upper level, we have a top view of this pivot arm. Talking about the grooves that were mentioned earlier, these were laser cut grooves, and the idea here was we wanted uniaxial motion. We didn't want drop off. We wanted it to stay straight because the tolerances are so tight. We'll have to look into ideal unrigidity, basically. We'll have to find out where we can find some repeatable flex. But the reason we did this was for rigid uniaxial motion because we have a distance to cover that can't be interfered with until you're there.
Yeah, so I mean, in this class, design class, so if you just told us that what's that property that determines elasticity property, so the material used opened up the window movement to a quarter or half an inch without any upper with that, but you just gotta address it, that's it.
Your thermometer's got a rubber
Yeah.
base with a,
Whatever.
When we tested it, we talked about it, we messed with it, so let it move through the acrylic being a plastic material, so we were doing that, apologies. Highlighting this here, this is actually the lower plate in that two-layer system. This is the groove that the temperature sensor is sliding along as it interferes perfectly, it connected perfectly with hardware that was already on the bottom of the temperature sensor. Yes.
and let me just say for you guys, don't go off and do a bunch more design work to make it flexible at this point. I mean, demo what you have at the end, if you all want to make some tweaks, it's really just not working. But don't go do a whole bunch of design work to give yourself more rigid flexibility.
When
Thank
it's
you.
fully extended, there is, I'd say, if I had to give you a ballpark number, probably goes a quarter inch up and down side to side.
Yeah, I'm sure it does. Nothing's not rigid.
Mhm.
And if you take a step outside of what we're doing, we had looked at a gimbal, but the problem isn't the center of rotation of the thermometer. The problem is the cable and how stiff the cable is. That controls where it's pointing when it's moving,
Yeah,
you know?
exactly.
We were gonna mount it on a universal axle, not universal axle, but
Again, lots of fun stuff you could do there, but you'll fail all your other classes.
Yes,
Yeah.
yeah, don't go do more design work, you guys.
all right, and the rack and gear actually slides along a groove in the top plate, and I'll explain the reason behind that here in a second. But that groove is on the top plate, temperature sensor grooves in the bottom plate. The reason the rack here is fixed to the top platform here is actually to allow dimensionally for enough movement, as well as keeping this and this to 6.3 inches. Initially, when we had this put together, this stuck out past, that's not okay, it's past the outside of the AGV. So in order to recess this further back, we had to invert the rack and pinion system, sticks to the roof so we can slide over top of this gear train effortlessly. In doing this, we also inverted this drivetrain in order to maintain the same gear ratio that we discussed in concept review that allows us to accomplish that distance. Any questions on that? If we're looking from the other side, talking about the sumo eye that we've demonstrated concept, looking at the different ovens and how it's doing that. So it's placed upon a rotating platform. It's actually on this axis of rotation. So we're taking advantage of rotational movement that's already in play, basically code that's already written, space that isn't being used. This allows for weight and space conservation. And at the end of the day, it's going to allow for accurate detection of each oven. Since we're literally pointing it where we're looking, there's only one thing in the field of view at a time. So, the consistency is going to be a lot higher than allowing.
Remind me again what you're using that for?
So, when we arrive at the cell, the first thing you have to do is determine which ovens are present and then service those ovens. So, when we get there, this sumo eye is going to rotate and look at all three ovens.
Gotcha.
And
So,
given,
but you're only looking at it to determine if it's there.
Correct.
Yes.
Just saying.
But aren't you don't you have available to you now information that would help you potentially, at least laterally know if there's any plus or minus misalignment between where you're sitting and where the ovens are that you could adjust for in your code? You don't need to go doing it.
Right, so it detects if something's there in field of view, but it doesn't really tell us where it's at.
So we're basically
As far as
getting a
left,
differential.
right. It just knows that it's in the field of view.
But you could make, what's turning it? Is it a servo or a motor?
It's a servo.
This servo is turning this gear train. It's actually the same one that drives the.
Does that servo provide positional data, like a stepper motor?
We do know how many.
Yes, we can tell it to go through this.
I mean, that would be a reason to use something more finer than the sumo that would actually tell you when you found the edge
Yeah.
versus is it there or not there.
I think what you're saying.
If you had to go do like that adjustment.
What you're saying is then given the amount of time that it took to get there, you could know your misalignment at that.
Or the number of encoders, you would know.
Base it off of the live
Yeah.
code.
Yeah,
That's a really good
it
idea.
is a good idea.
You can change based off of at least one
I think
dimension.
we've done that in projects in the past where we would look for the edge.
Yes.
Wait till we lost the edge, and then we'd know how many counts that was, and then we would go back halfway, or whatever you needed to, you knew exactly where you were. Yeah, I'm not so sure you couldn't do something similar to that here. It ain't worth trying. But that would eliminate, or potentially allow you to adjust for any lateral misalignments that you may have. It ain't gonna help you very much.
That's a great idea, thank you.
Can I point out
You
that
have fun too, here you go.
that's it? I mean, so that's a really good, valuable tool, why we have teams of engineers, not just one guy doing it all for himself, because you miss things like that.
All right, moving on to the lower level that I distinguished earlier. So we switched to a direct drive. We did this in order to eliminate unwanted forces and in order to conserve space, as this ended up getting allocated to the drives team. So we needed this in perfect alignment with the AGV in order to allow that space. And as well as previously, when it was situated here, it was driving it from the side, which was creating a moment and wanting to move that axle, which over time would have unwanted damages to the vehicle.
So let me throw something out here, I guess Bill will call it a timeout. Remember here, you're in critical design review, right? So you're trying to demonstrate to me, the panel, that you have a design that has low risk and that is, very repeatable, and that I shouldn't be worried that we can go to production with this, or at least low rate production. Right? So every time you start telling me how precisely this needs to be aligned with this and that needs to be precisely aligned with that, without me asking about it, you're kind of introducing a sense of anxiety for a systems engineer, right? That's going to accept this design. So just keep in mind, your objective is not necessarily to tell us all the great and wonderful precision, the decisions you've made in order to get this to work. Even though that's cool stuff, your job is to make us feel comfortable that this is a very viable system and that I should have no concerns that it's ever going to be a problem to operate or maintain.
Are you talking about, I said I had to be perfectly straight.
Yeah.
Hey, I didn't mean perfectly straight, I apologize for the bad wording, I just meant our previous idea, actually, because we have a dimensional tolerance back here where it goes to the mixing side, was actually had this at an angle.
Yeah.
That was another problem that we solved, I'll tell you about it.
Again,
There's actually tabs on this, we showed.
demonstrates your team and your intelligence and how you guys found and solved all these problems, right?
Yeah.
Which is, if this was a design class, I would be wanting my instructor to know all these things. Because I'm a smart guy, I want you to know, instructor, that I'm a smart guy. But in a CDR, I don't want to know that you had all these problems. I'd rather think that you knew right off the bat how this thing needed to line up and that it works and it's great, it's wonderful, right? So you're telling me all your dirty laundry from that you guys have been busting your hump for the last 3 weeks trying to make this thing work, right? You don't want me to know that. What you want me to know is that, oh yeah, of course, this is where it sits, this is why we have it here. It's going to be wonderful and there's no reason to be concerned about any of this kind of thing. Now, you get what I'm saying?
Yeah.
Now, if this was an internal review, we were all on the same team, and my role is what it is, conversations would be a little different. But if you're a company and you're selling to another company or to the government, don't want to instill any concern on the part of the buyer. Because the buyer is then gonna want you, well, I want another test done. I want you to run 14 of these and make sure that every one of these is lined up perfectly within the right tolerances. And then your program manager, like, you just cost us $100,000 because now we gotta run all these tests, kind of thing. So just kind of keep that in mind when you're doing CDRs, which you probably won't be doing for quite some time. Just kind of think about what's your role and what's their role, adjust your statements to work in that environment.
So let me ask you a question on that. So like CDRs that they would do, like if they would support equipment or one of those groups, I've been with you guys early on in their career. When they're given their design, do they want to give a little history, how they got there, or still focus on this is how it is?
Again, that's more of an internal thing, so I think you would get a little bit more into what you're saying, but you still would approach it like, you know, yeah, I'm aware that you're probably noticing that the tolerances here are tight, and so I want you to know that we've thought about that, and here's how we've mitigated that. You know, that's kind of how you approach it internally. Externally, I wouldn't bring that up unless the panel brought that up. If I said, wait a second, how tight does that need to be? Well, it's a great question. That's a great question. And here's what we thought through, and here's why we did it this way. That's kind of, instead of airing your dirty laundry, you don't need to air it, just let's see if they ask.
No, that's helpful. Todd, Angela, you got any other things on that?
I think it would be, it's a good learning process because from my perspective, you'll actually be sitting on my side of the table, probably before you're sitting on your side of the table, right? Because it's slowly, we're working with other vendors. So, just knowing that process, because you're gonna be the one looking for the tight tolerances. So, just think about it from the other perspective. I think that's sell this out.
Thank you.
The key is just, one of the keys is just understanding the elements. What's really the point? I mean, CDR, yes, that's the point, but from the perspective of internal, external, can drive some of the discussion, some of the comments.
Thank you. All right, any more questions on this one? Actually, I did have one more point up here. I wanted to point out this custom servo that was designed in order to conserve the same space and overcome this.
So you're saying now that I can have a stop sign?
Dude, to be fair, I was told, when I told you, I was told to tell you every cool thing and challenge.
Listen, we come here with one point in mind, and that is to make sure we point out anything. You cannot win for losing with us.
I knew as soon as.
We were told to tell you every challenge you. All right.
I did tell you that.
Yeah, literally.
We
I
had
had
Bill's fault.
I had a whole slide.
Everything is my fault.
All right.
Gladly.
Eric's gonna talk about our non-permanent neighboring place.
He designed a 3D printed funnel made out of PLA to be able to guide the temperature sensor into the oven consistently. As you said before, that is an inch in diameter with two different angles. The outer angle is 30 degrees, and the inner angle is 12. The funnel will rest on the oven with this right here and around the folding arm on this side here. And because it's in direct contact with the metal in the oven, we wanted to make sure that it wouldn't melt while the ovens were running. So we researched the melting point of PLA and found it to be 302 degrees Fahrenheit. With our, and the max possible degrees of the oven is 250 degrees Fahrenheit. And we extended the top of the funnel so that the stimuli, to act as a reflective surface for the stimuli, so for the oven detection.
So why the two different angles again?
I just show the back here to show where it's going to be sitting in the oven.
No. I mean the funnel angles. You got a 30 degree.
because we wanted, because we had to keep the slot open for the holes in the front of the oven. And if I had 30 degrees all the way down, it would be there would be an opening right here, like at the top of it.
Why not just a smooth parabolic type? Well, instead of bam, bam. Now you've created an edge, right? So when the thing's coming in, it's gonna be riding against that edge. Instead of, I guess it's gonna be doing that no matter what, but I mean, you've assumed that you have to print this thing with a linear angle, and then you're step functioning to a different linear angle in order to get to the right diameter, but you could have had a continuous funnel that just has a non-linear shape, right? Because you're 3D printing, that's the beauty of 3D printing, right? You can do a lot of things that's very difficult to do if you're machining. So you could have had a funnel that looked like that instead of one that's however you did like that, right? I was just curious if you guys had thought through that.
Didn't, honestly.
And no need to go changing it, just a funnel.
Any more questions on this? I'll pass it off to Will to talk about the brick 2 design logic. Thanks, Eric. Like Luke said earlier, and the other teams mentioned, there's 2 bricks. One brick we're in charge of, and the other brick Strive's in charge of. So this is the flow chart of how brick 2 operates. So up here on the left, you see beginning of the day, it starts up, sets with sensors, sets with motors, and then it does this function right here. It's called a task. So you can see there's this thing called a task, and it'll run simultaneously while your main program runs. So that's going to be constantly checking if the E-stop is pressed. It's a perfect time to bring up that we did this E-stop design.
So let me ask you a question.
Yes, sir.
Well, you're telling me that you've got a watchdog routine over here for your e-stop, but these guys have actually encoded the e-stop check at different segments in their code. Why the 2 different approaches?
Okay, so drives is a loop. It's a loop that continuously goes, and they check all of their sensors, and including the e-stop. So that happens very fast. The thing about brick 2 is that we have several very specific functions. It does what it does when it's at each cell.
Gotcha.
So
That's a good point.
right.
So you have to have your own separate loop watchdog kind of.
Correct, with a global variable, so that. So what I was gonna bring up here is this e-stop with, imagine a little button. When it's pressed, it sends one signal to 2 separate bricks. It does work. It's really awesome.
So what you're saying, you create a complex harness that we've got to now maintain.
Actually, it increases safety. Everything stops now.
So the problem that would introduce is if drives has an e-stop press while they're running, it sends that signal to us and it throws up our flag, our global variable that says, hey, the e-stop was pressed. So the way that we mitigated that was by making a function for us to check. Here. Drives, when their assistant situation is completed and they're doing their thing, before they move, they're going to send us a code via Bluetooth that says, hey, our e-stop has been pressed, it's resolved. We pick that up in our loop that's just waiting for a message from drives. It says, okay, we're turning it off. E-stop's not pressed. And like we kind of talked about a second ago, this little guy hanging out by himself. I'm sorry if you like flowcharts, he doesn't belong there. But it's important to bring up that 2 cells or 2 functions that actually have moving parts, 2 subsystems, because mixing has their moving conveyor belts. And we have our swinging arm and our extending thermometer. For every movement, we're going to check, see if the e-stop was called. Each and every movement. So it'll just call that e-stop, check e-stop function. Go see if it was called.
Is that e-stop, is that a momentary switch or is that a toggle type switch?
It's a touch sensor, so it'll be
Momentary.
So they throw, if they ever see it, they throw a variable flag.
So they become the toggle.
Yeah.
The latch.
Yep, so they latch a variable down.
That's it. Okay, well, we kind of covered it, but yeah, also in the beginning, if they coordinate with Brick One, we send a message, tell them we're ready to start the day. Then they finish their beginning day and do what Drives does, goes around the plan. And we go through this loop that we just talked about. And when Drives encounters a cell, they send us a message that they're properly positioned at each cell, and we call our function. If you're at the mixing cell, mixing function is called, that Matt outlined earlier. If you're at the molding cell, molding function is called. If you're at the data cell, data function is called, where it sends the data to the main computer. On completion of any cell servicing, you have this catch all, where it sends back a message to Brick One to say, hey, servicing is complete. You can go about your business. And we continue with our loop and just wait. Have any questions about the logical architecture? Brick 2.
So each time the other brick tells you what station you're at, you go through this loop and you just do it if then, instead of just calling a specific routine based on what they pass you, you're just going through and checking. So basically you've only got one routine for all of the stations and you're just checking what.
So it's like an if else if versus like a switch case.
It's just fine. In this case, it's fine.
Okay. No further questions. We do have a slide for the molding and data function. Would you like me to walk you through what they're going to do at each cell? Okay.
You guys want to see it? I think so.
I'm good.
All right, and again, the data cell. And then we're going to run verification tests. We're going to change whether ovens are present, so we can check whether they're not. And we're going to vary the temperatures so that according to the ICD, we can store the proper state of the ovens and transmit that out, including an over temperature situation. We're also going to press the emergency stop button at some point during our tests to make sure that it actually works.
So the only thing I don't see, did you have another set of tests to do?
No, sir.
So I don't see any part of this where you're varying your tolerance and your angles for those kind of things. So I would expect for you to, in addition to the various holding configurations, also look at some variation of being off kilter by some degree, plus or minus 5 degrees. I don't know. Maybe you want to let this thing back in a couple of times and see how much variability you're getting, and then test beyond that a little bit.
Okay, so the ICD does give them, tolerances as far as what they're supposed to hit, but that's a good point. So plus or minus 3 degrees is what is in the ICD, but
We never thought in our tests to include testing the tolerance limits.
right, that's a very good point.
Yeah,
Never thought of it.
I didn't see the drives team test that either. I mean, that's going to be a critical part of this, and we would want to see the test that says.
Makes perfect sense.
Since there's an agreed upon plus or minus quarter inch alignment at the cell, then we should test the far end of both sides.
That's right, yeah.
But then you guys need to be testing the fact that you can get within a quarter of a degree, whatever, quarter of an inch every time, at least maybe, 99 out of 100 times.
I don't think any of our tests thought to test, are we staying within whatever tolerances we were given? Like I didn't write them at the system level for the ones I did at the system for you guys.
And none of us come out of it.
Never even thought of it. I'm not sure. Really hard to say. Well, thank you.
Any further questions or comments, concerns?
Nope. Stuff, good stuff.
So now the team leads are gonna come up and talk about the subsystem interfaces. It was.
We're going to go over the physical interfaces of the different subsystems. This is a side view of the HV showing where those different subsystems will be located. As we see, drives is on the bottom here, right here. We have loading front and mixing encompassing the back half. We also have the top view showing volume mixing where they're going to be located now.
These are the ICD diagrams, right?
These are in the ICD.
Yeah. So here's your spot, Todd, when they get to them.
Also in the ICD, as Andrew was mentioning when he was talking about his section. Or with our object detection for drives, our ultrasonic sensor is located above the drives portion that we had previously stated. So we have in the ICD stating that drives has that portion in the molding subsection for our component.
So where in your sketches is that 2.215?
That is from the front facing back.
So is that on any of your figure 11, 12, or 13?
I do not believe that it is.
Because
So it would
you
be
mentioned it in your paragraph, so I was looking for that dimension on the figures and I couldn't find it.
you don't see it in there. So we missed that.
So that's 2.215
From the front of the HV. So this is looking at the front. 2.215 inches going back right. Yes, sir.
so go back.
Yes, sir.
So it's 2.25 from the left side, going to the right.
That'll be from this line right here. 2.215 inches back.
Really have to keep the MES.
Three decimal places.
3 decimal place dollars. Like, you don't really do that.
And this is one of the things we talked about last time, but when you specify 3 decimal places, that's really talking about some tight tolerances generally.
If I can step out of this.
Yeah. you can step
When we were going through the presentation, we did realize that we had done that again. And Dr. Forney actually pointed that out to us, I believe. And his suggestion was if we have the time to go back and fix that, then do that. And if not, then we'll take the hit of that. So we were taking
It's a learning experience.
Exactly. Yes. Anything else with the location of the different subsystems?
So with all of this being said,
Yes, sir.
have you guys have modeled this with all of these dimensions in place?
Yes, sir.
All right. So, yeah, I consider this a low risk.
Anything else on this?
So I have a question on that. Like in this day of modeling, if they had modeled things, had everything modeled, would they still create an ICD with all of these dimensions? Or would they say each vendor has the model with their areas noted?
I don't know how these companies are doing this nowadays.
Gotcha.
I think they're given an allocated area and they're told this.
In the model?
Yeah, there's probably multiple models, so there's probably a big
Uh-huh.
block model that says, here's your area, for your wing attachment or whatever.
Right.
It may be. And then they have to design within that, and if they're gonna exceed that, they have to go get with. If somebody needs to encroach on that area, I guess I don't know how that works, I've never done that, so
Yeah,
it's a good question. I kind of wonder that myself, on how they control that.
I saw source control drawings. They put in, yes.
so still drawings are being created for most of that.
And then for MQ8, we have drawings for a bunch of of our components, well, basically every part of the aircraft, and then we also have the CATIA model as well, that we reference them to.
Yeah, but think about when it was, well, it's a bad example because it's commercial driven, but think about when the helicopter was being designed originally from scratch. And your company was gonna go design the landing gear. I know it's the landing gear. And so you gotta have some area that you know that is your area from a structural standpoint where you can attach. I don't know how, if somebody else is designing the airframe, I don't know how they define that initially. And I would imagine it's probably a series, a lot of churn to begin with until they can get something kind of figured out. And then your program would probably say, hey, we need this torque box mounted right here. So you all give me a thumbs up and then, yeah, but then they probably incorporate that into the model. And then you can change your design so long as you don't get out of that box.
So that's, yeah, so that's, for most of ours, we end up with like source control drawings where the OEM will define what the critical points are or whatever. But we've even seen it where they've given enough free play in source control drawings that they'll change up like a locking feature. We had this just recently on a you can lock it any way you want. So we're getting all of these components coming in that have different locking features of how to lock the actual part in together, and it does make a difference. And they're like, oh, we didn't call that on the drawing. They can just use whatever they want, just as long as it doesn't rotate. And we're like, yes, but now that they've used this not to rotate, it doesn't interface appropriately with, you know, this tool that we have. So it was kind of, we started realizing that even though it met source control drawing for the vendor, and the vendor produced it, we have two different parts out there, we can only use one vendor part.
Oh, interesting.
We actually had to go just modify the tooling so we can actually.
That's still a little bit different than.
So
That's
from
what they
learning,
do,
it's-
is they just set, so they didn't give the vendor the model, they put together a source control drawing, said your part has to do this, and it has to interface this way.
that wasn't,
Here's your box.
yeah.
Yeah.
So I'm thinking from learning, it's probably still a good idea to take the time for the drawings.
So in CDR, drawings are everything.
Yeah.
Models, drawings are everything.
Okay, Nicholas, sorry.
Now that we've defined the space allocation, we'll go into the physical interfaces with the different subsystems. So with drives interfacing with mixing, we have the 4 holes that are located at these points that are dimensioned out. And with that, the mixing subsystem will be physically interfacing with the drive system using Lego connectors. So it'll be clipped into place, secured, but also easily removable if any servicing needs to be done.
I didn't really look that closely at this till Todd was saying, when he looked, he was confused what he would do. Just looking at it, like, how would I know those are my holes if I'm mixing? Because you got a ton of holes on there.
We put dimensions on those holes. That's what we were thinking would be enough to specify that those were the holes. We did not
You're
provide.
saying you're confused on the drawing?
Well, he was just saying, like, looking at it raw, you know, like coming in, knowing nothing. He wouldn't know what he was supposed to do to interface. And
But is, one thing, and I don't recall, but the items going into those holes, how many individual pieces are there, or is it a set that's going to fit right in? So, yeah.
4 holes on this side.
Okay.
So just
so the 2780 defines the pin. I think it's just more like clarifying which holes they're mixing. So again, you know, you think about that guy back at your plant who's never been here. All he's seeing is this. He will probably need just a touch more to know, okay, those are your 4 holes.
Like highlighting a certain color or something, would that be enough? Or would you just need to remove the rest of the holes and just have the 4 maybe on there? So
A lot of different ways you can do it.
Yeah.
But you guys, obviously, if you guys have worked as one big team for most of the project, so imagine if you weren't, imagine if one of you was in France and the other one was in North Carolina. You wouldn't have had that comm, so everything goes down to how do you define the drawing and how do you know what part of the drawing is yours?
Yeah. And I think probably what you said, Les, is you just give that
4 holes
subsystem
that
what
they
they
have.
need.
Your 4 holes.
Yes,
That
and the
makes sense.
dimensions for your 4.
We weren't really focusing crazy detail onto the drawings, as Dr. Pointing wanted us to focus more on the systems aspect. So I feel like we could just easily add in a flag name, same.
Highlight it.
Don't necessarily need to if it is that basically a plug and play of a couple of pieces.
Mm-hmm.
Anything else?
Nope.
Okay, so we'll move on to molding, which I can see there may be the same issues with this.
Sure.
But molding uses these 2 slots on the right side, these 2 slots on the left side. As they showed in their subsystem, they have tabs on the bottom. Those go through the top plate for drives. They'll be secured with pins that go through their portion to lock their subsystem into those holes. One more thing that I need to point out with this, the center line of the AGB, the blue line here, the center line that molding is using for their system with the molding cell is going to be 1.93 inches off of the center of that. And William will talk about that on the next slide. So I'll pass it on to Matt to talk about.
So for the interface alignment for mixing position, drives just needs to get the AGB in the mixing cell centered on that center line tape that we saw before, plus or minus the 1/4 inch tolerance. And they also need to back into the cell as we're located on the back side, and then just stop at the indicator mark with that 1/4 inch tolerance as well.
That's where we never thought to test. Add into our test, can you prove you're doing
Exactly.
that?
Any angular requirements, build upon any angular requirements? It can be centered at one end and off on the other. So where are you saying that the front and the back of the AGB has to be within 0.25 inches of the center of the mark, center of the line?
Just the side, for us, it's gonna be just the side closest to this.
Do you guys have an angular specification?
So we would need since.
Right, that's not here. It is in the ICD though.
Okay, that's what I was
The
thinking.
physical
They said
interface
no,
point,
and
so plus or minus 3 degrees.
We have that, is that for all of them?
It's for physically interfacing.
Okay. Okay. I was thinking that was just for molding.
No, that's overall.
Thank you.
Yeah, it looks to me like there's a lot of, the precision in this system is with the, what's the name of that group?
molding.
Molding. So a lot of that needs to be flowing down through your other groups. And I know a lot of times you don't even know what that is until later in the design process, but you still gotta have that communication process. So by the way, we need you guys to be spot on. But it's got a lot of time. Yeah.
Right, so like Nick said, we want the molding, we need the AGV to be lined up. Have our axis of rotation of our arm lined up with the center of the molding cell. So we need a 1.93 inch offset. They're gonna follow a tape line right down the middle. So we need that tape line 1.93 inches off so we can have our axis of rotation and we're in the right spot.
So. Time out.
Yes, sir.
Again, that 1.93 is real precise, but you got a 1/4 inch tolerance. So, plan is 1.9.
1.9, understood.
And we got this kind of tolerance band that should be well within the range of what meets your requirements.
I understand what you're saying.
You're saying like totally let 3 off because of the plus
Would
or
you?
minus.
No, because you could have extra stackable. So,
Okay, you got a tolerance of a half inch.
I know, but your tolerance is about around your center line. If the design for the center line is at 1.93, wouldn't your tolerance still be 0.25 inches around 1.93 inches? It's not a machining tolerance, it's an alignment tolerance. You know what I'm saying? I don't know for sure, but why would you arbitrarily drop the 300s off, even though you know that every X component out there is designed to be at 1.93? But you can interface it with a plus or minus quarter of an inch. So
In the real world, the more decimal places you have, typically drives to more QA or different kind of.
But this isn't a manufacturing requirement here. This is an alignment requirement. Where do you want me to point this thing? I want you to point it at 278.5 degrees, but it's okay if you're off a half a degree either way. If my vector has got to be 178 degrees or 178.5 degrees, I'm not going to tell you something different than that just because you can be off a half a degree either way, right?
In that case, but comparing that dimension to that tolerance is a half degree equivalent to that range you just said.
I think in this case, it's you have to be practical. Because like in this case, that's saying my maintenance guys have to have some kind of measuring device that measures 2 places. Because they're putting a piece of tape down and you're wanting them to measure 1.93. Well, they're using a tape measure. So that's not, that number ought to be a practical number with what you're asking.
but they already have to measure for that accuracy given the tolerance for the placement.
What's that?
They're both to the 100 spot.
Can't hear you.
I can't hear you.
Aren't they both to the 100 spot? So you're already required to have that level of accuracy as far as toolage goes.
I just have to have a tape measure with 1/4 inch on it.
Oh, I see what you're saying.
Yeah,
Yeah.
so it would be like a design consideration, thinking about the person using it.
Yeah. No, I think it's a great thought. I mean, the dimensions have to be, with that plus or minus, you have to be thoughtful. Okay, I don't really have to put that. Are you going to tell me to tell my maintenance guys to walk around with a caliper to put the piece of tape down?
Well, what about a fixed piece, like another, we don't have a permanent enabling device, but like a piece that says, hey, put it here, put your tape on here, like a jig, it's the same every time.
Yeah, you're right.
And you can, but that's another piece of SC I have to have.
Right.
The answer is, I don't know. I think the difference between manufacturing dimensions and tolerances and
But in this case, is where I'm putting a sensor or the tape,
this is telling you
When you take,
a piece of tape.
Or floor mark.
no.
Tape is offset in order to put our axis rotation.
yeah, the tape is
They're offset
offset.
the tape.
Yeah.
So it's still following it straight down its middle.
1/15/16, is that what it is? I mean, I think that's about what it is.
Yeah. You guys get the conversation.
So if I'm measuring something on 4, measure me 1/15/16. Plus or minus 1/4 inch. Is that what you're saying?
Yeah, I mean, I get what you're saying, yeah.
Yeah. Yeah, 15/16. If you wrote that on there, that's a tape measure. You can do 16ths on a tape measure. But you see 193.
But by the right, you gotta measure 1 to 15/16 plus or minus half inch.
Right. I know.
Yeah.
This is a very interesting philosophical question. Because I totally get Todd, it's a plus or minus a quarter inch, who cares? But then I also get Russell, well, you want it as close to this as you want, so you at least ought to start there.
Yeah, because it would change the stack, but.
Right, yeah. So I don't know what the right answer is.
I don't either. Not my area of expertise, so
No.
Todd's know better than me.
That's kind of what I'm thinking, because he deals in the mechanical world a lot more.
Everything should work if you have the right tolerance specified. If it's 1.93, 1/15/16 plus or minus a quarter inch. There's your band. I might just bring them in a little bit, so.
Yeah.
Doesn't sound quite so.
Maybe we need tolerances on our tolerances.
All right. Is there anything else for this?
I'm sure.
In this case, we'll move on and I'll pass it back to our lead engineer assistant.
I just wanted to cover one more thing with regards to the interfaces, which was our cable management plan. So mixing is housing the NXT bricks on the top. So we were the driver for this. So in the ICD, we've got these two images here. One is the bottom of our design and one is the top. And the bottom is basically showing this slot here, where the bricks will come through drives in this hole, come through the slot, and then they'll feed up and through these two top holes. And then from those two top holes, they can go straight into the NXT bricks. And Nicholas, if you would pull up the model real quick, I'll show where the cables will come through for molding. Thank you. So as you can see, we've got the slot here. They'll feed up through and then can come to whichever NXT. And then molding has this airspace here, and they're free to just come straight across to the NXT bricks. Any questions with the cable management? Very good. Thank you, Nicholas. This is just an overview of the weights. We mentioned those along the way, but we're just showing you here that each allowed weight is still greater than our design weight, so that's good. We're underweight capacity for each subsystem. The time allocations which we covered last time, we're still on track for those with our analysis of how long each task will take. Any questions on time or weight? Very good. And did you all have any questions overall? Left hanging?
Any thermal management considerations?
We, I don't want to say the wrong thing, but I'm pretty sure we talked with Dr. Bortney. Did we not? About the thermal, and you said don't worry about it? Do you not remember that conversation?
Not even the least. I remember, I couldn't even remember the student that was in lab last week, but.
I walked up and talked to you, said that.
Got it. So,
answer.
so what's?
You can't remember it exactly.
Yeah.
The NXTs or the other components overheating, right?
Yeah.
Was the concern.
Oh, gotcha.
And we chatted, Gavin and I chatted with Dr. Bortney.
I'm sure we did.
So again, I want to thank y'all for coming today. Just want to recap the project deliverables. Our last meeting was concept review. That was March 3rd. You gave us the approval to come to today, concept design review. And we are still currently on track and going to fulfill having a working demo device by May 3rd, along with our verification, testing, and data.
Sure you don't want to do that on Christmas Day.
So we know there were several concerns that we needed to still address within some verification testing. But do we have your approval to move into the manufacturing and production? Provided that we make those changes.
Yeah, with the, I think in reality, this will probably be what do you call it? Provisional approval, where you come back and would demonstrate that you've got the 3-inch, you know, walls inside the cells. I mean, that's just logic. And then, of course, we're gonna want those tests that we talked about added for demonstration purposes, but you're not there yet. So as long as those get added, then I think we'll be comfortable. Sure. The tolerance issues you want to talk about? Sure. All right.
Awesome. Did you two get those that he just mentioned? Well, with that, again, we appreciate your time, your comments, feedback, and on behalf of the team, thank you again, and we hope to see you with a very working design on May 3rd.
It's gonna be fun.
You hope to?
Yes?
An opportunity, general comments.
Yes, right now. So now's open floor, comment, presentation comments, design, anything.
All right, I have a note.
Yes.
So I like you directly addressed our areas of concern and made sure that you went through that. So kudos on that. Great job. I think everybody presented well again. So good on that. So here's what I struggle with the whole time. You guys need to note this. You guys have transferred a lot of risk in your design to the customer. So every time you came up with a design, oh, I have a design issue. Okay, well, the customer can have this additional piece of support equipment. And we're gonna take a phone. Hey, you know, there's multiple things that I've seen that drove that. So instead of you going back and looking at how do you reduce the risk to your customer and your design, instead, I think right, so the little flaps for the packet. Okay, well, we can't launch them right. Let's just we'll add some flags. So this right here is more risk and more for me to have to do as a customer, right? The tape, the alignment jig, great idea, but another great idea to transfer the risk to the customer, right? Kind of thing. Instead of making my design take care of those considerations, I've got to put more on my customer for them to be able to use my design, right? So I would be very careful of that. Those are the things that in the real world make and break whether or not you actually end up, you know, producing it or if we decide to buy it, right? The more you start to transfer that risk to the customer, the more the customer might decide, maybe I need to shop around again. So
Let me throw something in right here. You know, Russell's always saying this is not a design class. So for this class, you guys did great, but soak in what she's saying because you won't normally be designing like for this class. You will be designing. Those are great points because we did do a lot of that.
or you're sitting on our end having to figure out like because if you were sitting around going, wait, no, don't do that. You need to make your design take that into consideration instead of me having to go add something else, right? So and then sandwich that again with a good thought is that I can see that you guys were very diligent in what you did and how you were looking at it and tying it to the requirements, which I think is the purpose of this entire class. So you can see the thought that was put in that was evident 100%. Good job.
Overall, I think you guys did a good job. I think there is clear evidence of good communication across the team. That's goodness. But it is hard to separate yourself since you guys do work this close together from in some instances like we were talking about interface pieces. Making sure that that type of interface document speaks for itself because you guys just be working with each other every day. Good job. I think I'm seeing growth through the semester and how you're doing it, working, presenting it, learning. So that's good. Thank you.
Yeah, Mal did a good job all around. Don't take our comments personal at all. It doesn't really reflect on how well you did or didn't do. We're gonna find stuff just because we're not gonna sit here and not have some fun with you guys later.
Except my part, I should take that first.
You absolutely should, you're a PhD. But yeah, I mean, good stuff. Hopefully you guys are getting something out of this class that a lot of us didn't get a chance to get when we were going through school. So it's not a one-man show or one-person show. So,
Cool. Okay, any other questions for these guys? I've got one 8-bet rubric, if y'all wouldn't mind quickly filling out. In fact, we can run out there and let them.
thanks, guys.
I will be right back for you guys.
Collection.